We all want good measurements. It sounds reasonable when people are told to check out the quality of their measurement system before doing an experiment. A good measurement is one that has utility for the user. It is an objective method to assess the validity of a measurement system and minimize the factors contributing to process variation from the measurement system. A measurement system tells you in numerical terms, an important information about the entity that you measure. How sure can you be about the data that the measurement system delivers? Is it the real value of the measure that you obtain out of the measurement process, or is it the measurement system error that you see? There are three objectives for this training. Firstly, to explain various sources of measurement system uncertainty. Secondly, assessment of linearity, stability, repeatability, and reproducibility of a measurement process. This process is also called the gauge R&R. The conclusions drawn from all data depends on their accuracy of data. If the measuring instrument and the measurement method are not capable of making accurate and repeatable measurements, the data can have significant measurement error. In such cases, the conclusions drawn from the data are inaccurate and are misleading. Gauge R&R repeatability and reproducibility studies, also called gauge R&R, are the most widely used techniques for evaluating the variation in a measurement system and determining if the measurement system is acceptable for use. Once a measurement system is found acceptable, it is equally important to institute a formal system to manage the measurement system to ensure that it continues to be reliable and dependable. What is a measurement? Measurements are defined as the assignment of numbers to materials and their characteristics so that it could be controlled and their relationship understood. All measurements lead to errors, and we categorize them as two types, the random and the systematic errors. The random errors are caused by difference among the operators, equipment, time, and the environmental conditions. The systematic errors are the variance in reading from the measuring equipment from the reference master. The purpose of measurement system analysis is to qualify a measurement system for use by quantifying its accuracy, precision, and stability. There are two kinds of risks addressed by the measurement system. Measurement system analysis helps reduce two types of risks associated with the measurement of a process and making decisions. These are risk of false alarm and the risk of missed opportunities. But why do variations occur? There are several factors. Even when all the factors in a measurement process are controlled, repeated observations made during precision measurement of any parameter, even under the same conditions, are rarely found to be identical. This is because of the inherent variation in any measurement process due to the standard itself, the workpiece, environment, instrument, and the people and procedures involved. It is a good time to now introduce a concept called resolution. The resolution, or discrimination of the measurement device, also the smallest measurable value using this equipment. The resolution must be small relative to the smaller of either the specification tolerance or the process spread variation. As a rule of thumb, the measurement system should have resolution of at least 1/10 the smaller of either the specification tolerance or the process spread. If the resolution is not fine enough, process variability will not be recognized by the measurement system, thus reducing its efficiency. Every measurement is subject to some uncertainty. A measurement result is only complete if it is accompanied by a statement of the uncertainty in the measurement. Measurement uncertainties can come from the measuring instrument, from the item being measured, from the environment, from the operator, and from other sources. Such uncertainties can be estimated using statistical analysis of a set of measurements, and using other kinds of information about the measurement process. There are different types of measurement systems depending on the situation, each with its own methodology and purpose. These are based on coordinates or optics, scale, and sometimes vibrations. In a process, the measurement system is normally related to measuring the why, that is the reason why it is part of the measure phase in the Six Sigma process. Measurement systems analysis answers questions such as, can the measurement system adequately discriminate between different parts? Is the measurement system stable over time, and is the measurement system accurate throughout the range of parts? But from where do errors and uncertainties come from? Many things can undermine a measurement. Flaws in the measurement may be visible or invisible. Because real measurements are never made under perfect conditions, errors and uncertainties can come from measuring instruments and the item being measured. Variations happen, due to a variety of reasons. Some of these are listed here. Equipment, people, process, material, and also the system itself. When a part dimension is measured, the variation in the output is a combination of the actual process variation and the one due to measurement. The total variation you measure using a measuring equipment is the sum of process and measurement variance. Measurement system errors are of two types, one that impacts accuracy and the other the precision. Accuracy is closeness to the expected, and precision is the ability to be consistent to the expected. When making any measurement, it is normal practice to repeat the measurement in order to ensure that the data generated is repeatable. The reliable measurement. It is also important to make sure that the data generated is reasonably accurate by taking care to use measuring instruments that are calibrated. Then, when the same measurement is made by a customer, the data should be close to the figures generated by the manufacturer, that is to say, the data should be reproducible. It is only then that the data that has been generated is considered reliable. There are four kinds of measurement variation. The one that is needed as part of calibration is the bias, stability, and linearity. The one on the shop floor is the repeatability and reproducibility. Bias is the difference between the observed and the reference value. Stability is the consistency of measurements over time. Linearity is the measure of the bias values through the expected range of measurements. Repeatability or equipment variation is more than one measurements under exact conditions. Reproducibility or appraiser variation is the average of measurements when different operators measure the same part. The reference value, also known as the accepted reference value or master value, is a value that serves as an agreed-upon reference for the measured values. A reference value can be determined by averaging several measurements with a higher level of measuring equipment. Thus, a bias is the distance from the reference value to the observed average value. If there is a relatively high bias, it could be due to appraisers not following the measurement procedure, an error in measuring the reference value, or instability in the measurement. If the SPC chart shows a trend, the measurement device could be wearing or calibration could be drifting. Linearity is the difference in the bias values through the expected operating range of the gauge. In this example, the measuring instrument has more bias when measuring higher values. Bias 2 is higher than bias 1. Repeatability is the variation in measurements obtained by one appraiser with one measurement instrument when used several times while measuring the identical characteristic on the same part. Reproducibility is the variation in the average of the measurements made by different appraisers using the same measuring instrument when measuring the identical characteristic on the same part. Some measurements depend on the skill and judgment of the operator. One person may be better than another at the delicate work of setting up a measurement, or at reading fine detail by eye. The use of an instrument such as a stopwatch depends on the reaction time of the operator. This study compares measurement system variation to total process variation or tolerance. If the measurement system variation is large in proportion to total variation, the system may not adequately distinguish between parts. For example, how much of the variability in the measured diameter of a bearing is caused by the caliper? And can the measurement system discriminate between bearings of different size? There are three ways to compute gauge R and R. We will be continuing only with the average and range method. When using the average and range method, we need to compute the repeatability and reproducibility separately and combine them, so the objective here is to find the equipment variation and the appraiser variation. The experiment could be conducted by 3 operators and 5 to 10 parts. Each operator measures each of the part 3 times. Once this exercise is done, the equipment variation is estimated, followed by the appraiser variation. Thus the total variation is computed as the R and part variation. When the operator takes a part and reads a measure and repeats this many times, he creates a variation. Also, when the same is done by another operator, it creates another set of variation. This is now extended across all the parts until all of them are verified. A data sheet here shows a sample computation. One operator checks 3 times for computing for repeatability, and this is done by 2 appraisers to estimate for reproducibility. This is now extended for up to 5 parts to get an estimate of the part variation. There are several inferences from the gauge R and R. If repeatability is large compared to reproducibility, then the instrument needs maintenance or the gauge should be redesigned to be more rigid. The clamping or location for gauging needs to be improved. There is excessive part variation. If reproducibility is large compared to repeatability, then the appraiser needs to be better trained in how to use and read the gauge instrument. Calibrations on the gauge dial are not clear. A fixture of some sort may be needed to help the appraiser use the gauge more consistently. By comparing the standard deviation of measurement error with the specified tolerance for a particular product, we determine the relative utility of the measurement system for that particular product. Gauge R and R studies commonly define PT values that are less than 0.10 to be good, while PT ratios in excess of 0.30 are said to be inadequate. Any measurement system with a gauge R and R less than 10% is acceptable, while it should be rejected if it is above 30%.